In this module, we will discuss applications of Smith chart for some transmission line problems. As we saw in the last module, Smith chart is essentially a graphical tool that represents reflection coefficient on a real and imaginary plane, that is the Argand diagram. And from there, because there is a one-to-one relationship between reflection coefficient and impedance of the impedance on the transmission line, it is possible to represent impedances as well on this particular chart. As we have seen in the mini derivation of the Smith chart essentially consists of circles which are constant resistance and semicircles which are constant reactance circles. You can divide the Smith chart into two parts, the upper hemisphere and the lower hemisphere, or rather the upper plane and the lower plane. In the upper hemisphere, the reactances are all positive, therefore they would correspond to inductive reactances for a given frequency. In the lower half of the plane or the lower hemisphere, the reactances are negative, indicating that for a given frequency those would contribute to, or those would come from capacitive reactances. So let us look at Smith chart, and before we can look at Smith chart and its applications, here is what you should do if you want to get full benefit of this module. Pick a Smith chart. You can actually download Smith chart from internet, get a printout, get some of those Smith charts and be prepared with you. Then as we perform calculations on the Smith chart, I will not be actually using the actual numbers. I will actually leave that to you for you to enter those numbers. I will show you the procedure step by step, and I would request you also to carry out the same steps in your Smith chart, and in the next module or in the attached PDF documents, I will give you the answers to these problems. If you have followed all the steps that we discussed, first understand the steps of using Smith chart and then try out each step for the given values of the numbers that I will be using. Okay, and then you should obtain answers which I would upload on the course website. So it should essentially match, and if you get match within say 5 to 10%, you are all right, because Smith chart is essentially a graphical tool. It can only be used mostly to get qualitative analysis. To get quantitative analysis or to get quantitative numbers, you should actually plug in the formulas. Okay, but Smith chart of course gives you a nice intuitive understanding of how transmission lines would behave under different load conditions and some of the operations that you would be doing. Therefore the value of Smith chart is basically in its intuitive understanding of transmission line problems. Having said this, let us now begin to look at some of the applications of Smith chart. Before we do that one, let us review something about reflection coefficient. Okay, we have looked at reflection coefficient, but I would like to just point out a few things about reflection coefficient which actually form the basis of Smith chart as well. Okay, so you have a transmission line of some length L, let us say. Okay, these indicate that this is a two conductor transmission line, and these nodes which I have left it open circle nodes would indicate the end of a transmission line. If this is not looking like a uniform transmission line, please excuse my drawing. These two lines are straight and supposed to be parallel with each other. To this transmission line you connect a load. The load could be complex, right? So if the load is frequency dependent, as it would happen if you are exciting the transmission line with a sinusoidal signal, and for that frequency the load might be inductive, capacitive and conductive or resistive, right? So you will have ZL typically to be a complex number, and let us assume that Z0, the characteristic impedance of the transmission line, is given by Z0, and for all the cases that we are going to consider, we will be considering lossless transmission line. Okay, so we will assume that transmission line is lossless. This implies that Z0 is real, okay, and the propagation constant gamma will be purely imaginary, that is attenuation coefficient is equal to 0. Okay, now we will substitute this condition later in a few minutes. To the sending end you might find a generator impedance and a generator voltage. These terms of generator impedance, generator voltage and the fact that this is a generator comes from an older terminology of transmission lines where the source was usually called as a generator. Okay, so on the Smith chart as well you will see scales which talk about wavelength towards generator. Okay, now this is the load portion. Okay, the load, as I said, could be complex. The transmission line has a length L, one of the coordinates that we use would be to measure z axis from the source end. So at the beginning of the transmission line you call this as z equal to 0, therefore the end of the transmission line will be at z equal to L. Now frequently in transmission line problems you actually are going to change the length of the transmission line. So you want to, when you are doing impedance matching or when you are just connecting the load but you don't know, you want to optimize the length of the transmission line. So this L is usually not fixed, okay. Load is usually fixed, okay. So you have an antenna at this position. Now you have to connect a transmission line, do couple of transmission lines in between so as to match this load, to match the input impedance to that of the generator, something that we will be talking about it later. So the transmission lines could be multiple and the lengths are not usually fixed. So to specify such situations, it is common to actually consider the distances from the load by defining a variable d. How is it related to z? Z is L minus d, okay. So what happens to z equal to 0? This implies d is equal to L, that is your L units away from the load. So d axis goes in the opposite direction as that of L, okay. So z equal to 0 corresponds to the source or the generator, okay, which would be L units of distance from the load, okay. So z equal to 0 is the source or generator and this is L units from the load. Z equal to L corresponds to the load plane, correct, because z equal to L in our original coordinate system would correspond to the load plane. But z equal to L implies that d is equal to 0, which means that you are actually at the load itself, okay. So d measures distance from the load, okay. So keep this in mind, whereas z represents distance from the generator, okay. In cases where you know the generator is given and you want to select the load at a particular distance, then you actually use the variable z. But in most cases you would be using the variable d, which would measure the distance from the load, okay. Now at any plane on the transmission line, okay, there would be incident as well as reflected waves, right. So there would be incident waves which is V plus and there would be reflected waves which is V minus phasor. And what is V plus phasor? V plus phasor is some amplitude V0 plus e to the power minus gamma z. So I am for the time being using gamma, but later I will substitute gamma equal to j beta, okay. And what about V minus? V minus is V0 minus, which is the reflected wave amplitude, and it is propagating along minus z direction, therefore I am writing this as e to the power gamma z. Now reflection coefficient at the load is defined as the ratio of the reflected voltage amplitude to incident voltage amplitude, okay. So this is the reflection coefficient at the load. This itself would be complex, okay, because this is actually connected to ZL and Z0 and ZL could be complex. So this reflection coefficient could be complex number which can be written in its magnitude and phase as magnitude of gamma L times phase phi L. Now if you go back to the way in which gamma R and gamma I are represented, right, so gamma R and j gamma I are the gamma plane representation of the reflection coefficient. You can represent this gamma L e power j phi L by drawing a straight line, okay, of magnitude gamma L, okay, and at an angle of phi L as measured from the horizontal axis, okay. So this is how you would actually measure or you would actually represent, okay. So you would represent the reflection coefficient, which is a complex number, on gamma R and j gamma I. In fact, this is essentially Smith chart representation as well, because you remember Smith chart is nothing but circles and semicircles defined on this gamma R j gamma I plane or the complex gamma plane. So this is the load reflection coefficient, but what is the reflection coefficient at any plane? You imagine taking a particular plane here as shown in the red axis. There is an incident wave V plus, then there is a reflected wave V minus. The ratio of this V minus to V plus at any plane Z will give you the reflection coefficient at that particular plane. So substituting for V minus and V plus from these expressions, what we see is this is V0 minus e power gamma z divided by V0 plus e power minus gamma z. But I already know that ratio of V0 minus to V0 plus is nothing but gamma L. So this is gamma L e to the power 2 gamma z Substituting for gamma, I can write this as e to the power 2 alpha, and substituting for z, I can write this as L minus d e to the power j2 beta L minus d. Okay. Now we also utilize the fact that gamma L itself could be complex, therefore I can write this as magnitude of gamma L, okay, e to the power j phi L, then you have e to the power minus 2 alpha d, you have e to the power minus j2 beta d, and then you have e to the power 2 alpha L e to the power j2 beta L, correct. Now there are certain things which are dependent on L, so I can actually group them together. So these quantities I can group them together, okay, and call this as some gamma with a subscript L. Please note that this is not the capital L, okay, capital L stands for the load and small l stands for this constant phase factor. This is a constant phase factor, right, because this is alpha if you fix, beta if you fix, and L is the fixed transmission line length, therefore this would essentially be some constant phase factor. Okay, so to take that into account, I can actually put them down as gamma L. Okay, I still have this e to the power minus 2 alpha d e to the power minus j2 beta d, and this is a phase angle which is changing as you go from load, because d increases as you go away from the load. Okay, so this would be the phase angle which is changing, but what is the angle there? It is actually minus, so which means that you should be going clockwise, okay, as measured from wherever the starting point for gamma L that you would be there, which is this gamma L. Okay, so please note that this is actually gamma L. Okay, so with this gamma L, which is already making an angle of phi L plus 2 beta L, right, and has an amplitude of gamma L into it 2 alpha L. Okay, so this angle it's already making, and then you move this one away. Now suppose you assume that the line is lossless. Okay, suppose we assume that the line is lossless, then what happens to gamma of d? Because this z dependence has been replaced by d dependence, right, because we replace z is equal to L minus d, right. So if you actually write like this, what you will see is that gamma of d is equal to gamma L, alpha is 0, therefore this term will be equal to 1. Okay, so you have e to the power minus j2 beta d, but what is gamma L? Gamma L is nothing but gamma L magnitude, right, times e to the power j phi L itself, because if you are looking for this one, then alpha is equal to 0, right, so there is actually e power j2 beta L. Okay, but this e power j2 beta L is essentially a constant phase that does not really matter to us, right. So what actually matters is, as you go away from the transmission line, what would be the way in which your magnitude of gamma d changes, right. So you can actually obtain that by taking the magnitude of this one and then writing the phase angle for this, right. So if you take the magnitude, you are going to get gamma L magnitude, which would essentially be gamma L, and when you write the phase of this, you would obtain e to the power j phi L minus 2 beta d. Okay, so going back to the representation of gamma L on the plane, this would correspond to, this is gamma r and this is the imaginary axis j gamma I. So you draw a line, okay, of length magnitude of gamma L, which would be the load reflection coefficient, and the magnitude of gamma L would essentially be the same. Okay, this initial angle will be phi L, okay, so that you are actually representing this gamma L magnitude e to the power j phi L. Now at any point d on the transmission line, d units away from the load, your new value of gamma will be something that has to be clockwise moved on the constant gamma L circle, right. So you assume that there is actually a constant gamma L circle up there. Okay, this may not look like circle, but please excuse, but the point here is that on this constant gamma L circle, because see, the magnitude is not changing, only the phase is changing, and if you move a distance d away, your total phase angle must be reduced by an angle of 2 beta z. Therefore your new location would be the same magnitude gamma L. Okay, so this is the same magnitude, but a total phase change of minus 2 beta d. Okay, or rather if I consider minus as clockwise, so this would be a total phase of 2 beta d. Immediately you can see certain ramifications of this one. For example, since I know that beta is related to lambda as 2 pi by lambda, so the total phase change as you move a unit of d away from the load on the transmission line, right, the total phase change would be 2 into beta into d, which is 2 into 2 pi by lambda into d. Okay, suppose you move d equals lambda by 2 away from the load. Okay, so with d equal to lambda by 2, what would happen to the phase change? 2 into 2 pi by lambda into lambda by 2. So lambda cancels, 2 also cancels, and you get 2 pi, which means that after moving around, okay, so after you have moved around a lambda by 2 distance from the load, you are actually back to the same position. Now this actually makes sense, right, because we know that successive maxima or successive minima are repeating on the transmission line with a periodicity of lambda by 2. Therefore, this lambda by 2 bringing back to the same point actually makes sense, and this is calibrated on the Smith chart. Okay, so on the Smith chart, if you look, this value on the outer scale, which is called as WTG scale. Okay, so on this WTG scale, this is 0, and then as you go around, this would be 0.25, and clearly as you come back to here, so somewhere it would be 0.49, and then go all the way up to 0.5. So 0 and 0.5 are essentially coinciding on each other. Okay, so this is essentially what I wanted to tell you. As you move on the transmission line, your reflection coefficient magnitude does not change. In fact, the movement can be visualized by drawing a constant gamma circle. Okay, by drawing a constant gamma circle, and all the movements are actually made on this constant gamma circle. Now, constant gamma actually implies a constant SWR, right? So because there is a relationship between the two, you know that this would essentially correspond to constant SWR. Therefore, constant gamma circle is also constant SWR circle for that particular transmission line. Okay, again it is important to note that we are dealing with only lossless transmission lines. If not, it won't be a circle, it would actually be a spiral. Okay, if for example your alpha is non-zero, then from this point you would actually have dropped down to this point. Okay, so it would essentially be a spiral, and at the end point the distance, I mean the length of gamma L would have been reduced by a factor of exponential 2 alpha d. Okay, so that's essentially what this particular spiral thing is, but anyway we are not going to consider the lossless case, so this is not in any way important for us. Okay, so we are not going to look at this particular lossy case. Alright, so bringing back, constant gamma L circle is constant SWR circle. Now here are a couple of other things that you can immediately note down. What is the maximum resistance on the transmission line? The maximum resistance or the maximum real part of the resistance would be the transmission line characteristic impedance Z0, which is again assumed to be real, times SWR. Okay, this was an exercise which I gave you in the last module. I hope that you would have solved this one and realized this. Okay, because on the Smith chart all impedances are normalized with respect to Z0, what you would actually find is not R max, okay, rather R max normalized, and I am denoting this normalized by writing a bar over this. This would actually be equal to R max divided by Z0, normalizing with respect to Z0, and you would see that this is nothing but SWR, right? So the maximum R max would actually be equal to SWR. Similarly, the minimum impedance or the minimum resistance is given by 1 by SWR normalized. Okay, and where would you find SWR? SWR is actually on this particular axis, right? Because you can actually look at what is the maximum R, and maximum R would happen over here, right? On the Smith chart, the maximum impedance, okay, occurs on this side. So if you assume that this is the center of the Smith chart, then this would be where the constant circles are located. On one of these circles there would be an intersection which would correspond to the SWR point. Okay, the minimum points would happen on the circles in which R is less than 1, and let's say this would happen at 1 by SWR corresponding to the normalized minimum impedance. So we have understood much about reflection coefficient and some basic manipulations on the Smith chart. Now we are going to actually put all these things together to solve certain problems, certain typical problems. For these problems you may assume that Z0 is 50 ohms, okay, line is lossless, okay, and I will give you the other numbers as we go along, okay. But first let us look at what kind of problems can we solve, okay. So let us look at the first problem, which actually is not really interesting in the sense that we don't normally use Smith chart in order to solve this problem. The problem is find gamma L, the reflection coefficient reflection coefficient of the load given ZL and Z0. Are this information enough to solve for this problem? Yes, actually you can use the formula. The formula straight up gives you the answer, gamma L is equal to ZL minus Z0 by ZL plus Z0. But if you want to use Smith chart, okay, so I'm going to draw some representative Smith chart over here, okay. So these Smith charts may not look very nice, but they are just used for illustration purposes, so they are not accurately drawn. You should get hold of a Smith chart which is accurately drawn, okay, and then follow all these steps that I am talking to you about. Let me also color up one circle which I am going to call this as unit circle. This unit circle means R is equal to, this red circle which I have drawn is essentially a unit circle, okay, and this point is the center of the Smith chart. Let us denote that one by O. You remember that all these are constant R circles and these semicircles are constant gamma circles. You should also remember that this axis is the open circuit, or sorry, this point is the open circuit and this point is the short circuit impedance. And if you look at Smith chart carefully, you will actually see some very interesting things, okay. So on the outer scale you actually find two scales or two circles, okay. One circle is called wavelength towards load and it would be going, the wavelength towards load would be going this way, okay. So let's write down it like this. So this is your wavelength towards load circle, okay, and there is another outer circle which is very important for our case, which is the wavelengths toward generator. Now why is that? So this is the wavelength towards generator and it would actually go in this particular direction, okay. So it would actually go in this clockwise direction, okay. Now what is the significance of this wavelengths towards generator and wavelengths toward load? What it simply means is that since gamma changes its phase as e power minus 2j beta d or j2 beta d, doesn't matter, this d can be expressed as fraction of lambda, because beta is 2 pi by lambda. Therefore if you express d as fractions of lambda, let's say this is 0.2 lambda, then that lambda would cancel and you would get some reasonable numbers. Therefore all these scales are calibrated with respect to lambda, okay. They are not calibrated with respect to Z0. So you should explicitly calibrate or normalize all of your impedances using Z0, okay. Alright. So the problem that we want to solve seems to be that I want to find out what is the reflection coefficient given ZL and Z0 using Smith chart, okay. The first step in this is to enter or normalize ZL, okay. Let us put a bar over this one to denote that this is normalized value, or you can use a small case z, since that is difficult to distinguish in this paper, in this screen. I am going to use a bar to indicate that this is normalized quantity. So normalized impedance is nothing but ZL divided by Z0, and there is no units for this normalized because Z0 is in ohms, ZL is ohms, therefore ZL bar is dimensionless quantity, okay. This is just a number. So you enter Smith chart, okay, you enter Smith chart with ZL bar, okay. Let us consider a simple example. Let us assume that I am looking at, say, ZL of 100 plus J200 ohms, okay. Please note this is ZL and it is in ohms. So this is ZL which is 100 plus J200 ohms. Therefore the normalized ZL will be 100 by 50, because that is what the value of Z0 that we are assuming, plus J200 by 50, which is nothing but 2 plus J4. So on the Smith chart you locate R equal to 2 circle. So let us say this is R equal to 2 circle. Also locate plus J4. Now plus J4 is inductive reactance, therefore it should occur on the upper half of the plane. Okay, so let us assume that this is your J4. So your initial point that you would be there on the Smith chart would be this one. Okay, so maybe we should use a different color here. So let me use this blue color to denote this point. Okay, so this point let me also call as P2. Okay, and P2 denotes normalized ZL bar. On the Smith chart, P2 denotes normalized ZL bar. Please note that I am just doing this one on a qualitative basis. You should have your Smith charts in hand and you should carry out these steps as we are carrying out. Okay, but don't rely on these diagrams too much. I am just going to show you the steps and you should actually enter the values. I will give you the answers in the next, in the attached PDF document in the course website. Okay, so you actually end up with first P2 on ZL, and from the center of the Smith chart you should now draw a line which passes to P2. Okay, the angle which this line makes will be the phase angle phi L. Remember that 2 beta L is not of any consequence to us, therefore I have removed the 2 beta L from consideration. So whatever the angle that we measure of this line, right, which would also give you the magnitude of gamma L. Okay, so how does it give you the magnitude of gamma L? We know that the outer circle on the Smith chart must be, sorry, this is not even looking like a circle. So let's say this is the outer circle on the Smith chart. This has the maximum radius. So on the Smith chart, let's say this is about 3.2 centimeter. Okay, so you decided to print the Smith chart on a paper, and then on the paper it came out to be 3.2 centimeter. Now this magnitude of gamma L would be the fraction of this one, right? So let's say this is magnitude of gamma L. Okay, measure this using a scale. Okay, and then so let's say you measure this one and you found that the value here is delta, and then normalize this one by the radius of the outermost circle. Please note that on the Smith chart there are two outermost circles, one is WTG scale and the other one is WTL scale. We are not talking about those circles, we are talking about the Smith chart R equal to 1 circle. Okay, so outer this there are still two more perimeters circles, don't worry about those. Okay, these are WTL and WTG scales. So once you get delta, normalize it with respect to 3.2 centimeters. I mean, I am assuming that this radius is 3.2 centimeter, but on your Smith chart you have to measure what would be the radius. Okay, so this is on the R equal to 0 circle. Okay, so this would be delta by say 3.2 centimeter, and that would give you the magnitude of gamma L. The angle that this would make will give you the phase. So your reflection coefficient is gamma L e power j phi L. Don't use this procedure. There are also axes calibrated down which tells you the magnitude of gamma L as well as the phase angle phi L. So all you have to do is to take a compass, okay, measure this distance and then cut these two axes with that particular compass distance. Okay, so when you do that one, you can directly read out what is the value of magnitude gamma L and the phase angle phi L, that would be in degrees. Okay, so this is an application of Smith chart, not widely used because the formula is more convenient in this case.